This lecture is going to be an introduction to propositional logic. Now, the first step is, what is the set of propositions? So if we're going to talk about propositional logic, we first must know what is a proposition, or what is a valid proposition. So we're going to be talking about well-formed formulas. Now, these will be inductively defined, and in the previous lecture video, I defined inductive sets, so you can sort of go there, but the basic idea was there's a universe set, a core set, and a set of operations, and the inductive set is the minimal set containing the core set, which is a subset of the universe, which is closed under the operations. Now, side note, let's say, which will be important, by the way. How do I prove properties about inductive sets? The way we're going to do this is via structural induction. So let P be a property of members of some universe U. Then if I have two things, so if firstly every member of C, which is our core set, if every member of the core set satisfies the property, satisfies P, and if F is in O, then all elements of P1, P2 in the universe, if any two elements in the universe set which satisfy P have the property that operation of P1, P2 satisfy P. So sort of, this is, for example, in the case where the operations are all taking two inputs. So if any two inputs which satisfy P means that the output, and I mistakenly wrote O here where it should be F. So if for all the operations, if the two inputs satisfy P, then the output satisfies P. We have that I, U, C, O, all elements of this inductively defined set satisfy P. And you're going to have to go to the previous video if you don't understand what IUCO means. Now, if we want to just sort of extend this, taking n inputs, so I'm now adding this condition that instead of the function taking just two inputs, it will take n inputs. And it's pretty simple. All you have to do is you just extend to n elements, like n elements of U which satisfy P. Then this function f applied to these elements will satisfy P, and then you have the same result. Okay. Now, back to propositions. So now, what is our universe? What is the universe of propositions? Now, we're going to say the set of all strings over the alphabet with the following symbols. Now, I'll just put like a sum here, just sort of to indicate, which is common in sort of other fields, such as computability theory, where you talk about DFAs and things like that, and other formal languages. That this is a formal alphabet, which just means a set of symbols, or just a finite, some kind of finite set. Or actually, that doesn't have to be finite. In our case, it will not be finite. Now, there will be three types of elements in our alphabet. First will be variables, which will be P with some sort of subscript. So this N will be some sort of number, natural number. So P2 ... And this will be infinite. And now we'll say logical connectives. And this will be the standard stuff, not the not connective, the and, or implies. Yes, implies. And, for now, these are just symbols, by the way. So don't think of these as having a meaning, but rather think of them as just symbols in our alphabet. And since we're formalizing this, there will be something called punctuation. And this will be the symbols open bracket, close bracket. And just to make it sort of clear what I'm writing, is I will do this. So the actual elements are open bracket, close bracket. Okay, so these are all the symbols, and our universe set will be all strings, all finite strings over this alphabet. Okay, so for example, in our universe set, we could have something like P1 and P2. So this is in the universe. But we don't want this. As in, this is not a valid proposition. Or at least we don't want it to be. Because we can't really say it's not a valid proposition, because we actually haven't defined proposition, and that's our goal here. So we're going to define proposition such that this is not valid. So what we are going to define is I, U, C, O, such that define, let's say our goal is to define ICO such that, or more precisely define UCO such that IUCO is our desired set of propositions. We already have U equals this alphabet, which we've already defined. Now, C is our core set. So what do we know is a valid proposition? It's going to be Pn. So any of the propositional variables. Now, what are our operations? Oh, so what we want to have is that a couple things, okay? Set of operations. A, let's say if alpha is a proposition, then we want open bracket not alpha to also be a proposition. Okay? The second thing which we will want is if alpha and beta are both propositions, then we want open bracket alpha and beta close bracket to be a proposition. And remember, this is syntax, so the brackets matter. As in, we cannot say that this is a proposition. We want to formally define what a proposition is syntactically. And similarly, if alpha and beta are propositions, we want open bracket alpha or beta close bracket to be a proposition. And another thing which we will say is if alpha and beta are propositions, then we want alpha right arrow beta close bracket to be a proposition. Okay. Now, this is our desired set, and now we're just going to explore some syntactic properties of propositions. Okay? Now that we've defined this, we have a formula or a process for writing proofs related to propositions. And what is this process? This process is the same process which I defined above, which is to use inductive structural induction. Okay? A couple basic properties. Every well-formed formula is either a propositional variable or starts with left bracket. Okay? You can attempt to prove these. I will not prove them here. If any of you guys have questions, you can ask me and I can go through the proof if you guys struggle. These should be fairly straightforward if you follow the procedure of structural induction. In every well-formed formula, and when I say well-formed formula, I just mean this formal definition of a proposition, the number of left brackets is equal to the number of right brackets. And the third thing, in every proper initial segment, which means a substring of a proposition, or let's say of a well-formed formula, which, and let's just to be completely clear, a contiguous substring of a well-formed formula, which starts at the beginning of the string. The number of left brackets is strictly larger than the number of right brackets. A contiguous let's say, a contiguous proper substring. And now we'll just make this bold, just so that it's clear that it has to be proper. Otherwise, this is not true. And if it did not have to be proper, then this would be easily disproved by the second property, because in every well-formed formula, the number of left brackets is equal, so it's not strictly larger than the number of right brackets.